Hello. Here determinants will be defined and some important properties will be formulated for them. Determinants are numbers, numerical quantities associated to square matrices. There is nothing like that for non-square. Matrix has to have the same number of rows as of columns. And verbally, a determinant of a square matrix is a sum of products of n entries, all taken from different rows and columns. With signs. So that is a rather informal but still a useful description of a determinant, which helps in understanding how to compute it. Proper mathematical definition will be the following, but it will follow this general slogan thing. Since we're taking products of matrix entries from all different rows and columns, we always have to take something from the first row, and the first index is just the row index, and then the second is a column position, which I'm writing as sigma 1. And in the product, I'll have to take something from the second, again, situated somewhere in the second row in the column number sigma 2. And all the way down to the last row, which will have an element taken sitting somewhere in some column sigma n. Since these factors in the product will have to be sitting in different columns, the sequence of column positions, sigma 1, sigma 2, and so on, sigma n, denoted here like that, will have to be a sequence of all different numbers. Such sequences are nothing but records of permutations. The set of all permutations of n things is capital S sub n, and then sigma will be running through all such permutations. And the summation sign is saying that we're taking such products and then we're taking the sum of them. But the products will have to come with signs determined by the positions of the factors. And the sign rule is just the sign of the corresponding permutation. So that is now a complete definition, precise mathematical definition of the determinant. It's a sum of products of matrix entries taken from different rows and from different columns with sign, which is the sign of the corresponding permutation. So let's unpack this definition for concrete sizes. The easiest of them is just size 1. The matrix is just a number. The determinant of such matrix is that number. When size is 2, the matrix, according to these notations, will have 4 entries labeled like that. And then the determinant of that matrix will be sum of all permutations of 2 things. And we have to imagine these 2 permutations. The 2 things can be permuted in 2 ways. Graphically drawing these permutations, we have the permutation which doesn't permute and the permutation which changes 1 and 2. So this 1 goes to 1 here, and 2 goes to 2. In this case, for this permutation, 1 and 2 change their places. then this permutation corresponds to a product of matrix entries, and the rule is, okay, sigma of 1 is 1, so we take a 1 and 1 again, because the column position is sigma of the first. And 1 corresponds to 1, and 2 corresponds to 2, so we have to take the product of these two matrix entries, and the sign of this permutation is +1. So the sign of the product is also plus. This permutation encodes the product of 1, 2. 1 goes to 2, 1 corresponds to 2, so the entry in the first row in the second column has to be taken, and then the entry in the second column has to be sitting in the first row. The sign of this permutation is -1. And so is the sign of that product in the determinant. And perhaps using different notations for matrix entries, A, B, C, D for the 4 entries, we can rewrite the answer as AD minus BC, which came across in a couple of computations we did before, like solving a linear system, 2x2 linear system. This was appearing as sort of universal denominator in the answer. The non-zero property for that determinant was crucial in distinguishing between unique solution and multiple or no solutions. So that is the reason why determinants are important at all, because they appear in many questions related to linear algebra. Let's continue with unpacking the formula for size 3. So this time I have 9 matrix entries, and I have to use indices, it's easier. The number of summons is the number of permutations of 3 things. There are 3 factorial, 6 such permutations, so I will have to accommodate 6 products. They are corresponding to permutations, so I have to list all possible permutations of 3 things. I can do it graphically, or I can do it tabulating the permutation. I will do both. So here I will start with the easiest identity permutation. Here's its graph. Its table is like that. 1 corresponds to 1, 2 to 2, and 3 to 3. And the corresponding product of matrix entries will be from the first row, we have to take the first element, A11, from the second row, the second, A22, from the third element, 3, 3. The sign of this permutation is +1. The easiest way to see the sign is to look at the graph and make sure that the graph doesn't have multiple crossings, and then the number of such simple crossings will be, the parity of it will be determining the sign. The next permutation I will list is, again with sign plus, is what is called a 3-cycle, graphically looking like that. The table will be 1 goes to 2, 2 goes to 3, 3 corresponds to 1. Again, the sign is +1, and the corresponding product of entries in the matrix is A1, and the column position has to be 2. A2, the column position is 3, A3, and the column position is 1, and the sign is still plus. So next is the other 3-cycle, when we have this graph, and the table will be 1 going to 3, 3 going to 1, and 2 going to 1, and 3 going to 2. Again, the sign is +1. The product is A1, 3, A2, 1, A3, 2. Then there will be 3 permutations. The remaining 3 permutations will have sign minus, and they will be this permutation, this permutation, and this permutation. So they are all just permuting 2 numbers from 1 to 3 and leaving 1 fixed. 1, 2, 3. In this case, we are swapping 3 and 1. 2 is fixed. And for this, what is called transposition technically, for such a permutation, 1 and 2 swapped. 3 is fixed here. 2 and 3 change places. 1 is fixed. Again, the signs are all -1, so all the 3 products in the determinant corresponding to these permutations will have sign minus. Here, the positions of factors in the product are like that. The first row should be taken, the third element of A13, and the second row, it's the second position, and the third, it's the first. Here, A1, 2, A2, 1, A3, 3, and finally A1, 1, A2, 3, A3, 2. That is it. That is the complete formula for the determinant of 3 by 3 matrix. Let me also draw positions of the factors in the product where they sit. So here they're all taken from the diagonal. That is the product we're looking at first. Second, for the 3 cycle, we have 1, 2, 2, 3, and 3, 1. And the other 3 cycle is sort of symmetric with respect to the diagonal product of these 3. And then with minus sign, we have anti-diagonal, and here we have the product of these 3, and the last one is sort of symmetric again with respect to anti-diagonal. That is a good mnemonic rule of remembering which products we take. This is the same as listing on permutations, but sort of easier to remember. We have the diagonal with plus, we have the triangle around the diagonal with plus, we have another triangle symmetric with respect to the diagonal to this one with plus, and for anti-diagonal we have things with minus. That is probably as far as we can safely go. For the size 4, the determinant will have 4 factorial summands, 24. Half of them, 12, will come with sign plus. The other half, the other 12, will be with sign minus. Just too many to list in general. But yeah, 24 terms is a determinant strong enough. But what we can do in general is to, for a special shape matrix, is to just using this definition, this recipe for the determinant to find the answer. So that's what I'll be doing. First, for the identity matrix. The identity is a square matrix with all entries being 0 apart from the main diagonal where we have 1s. And then if we look at, because so many zeros are in the matrix, most of the products will be 0. So if we look at which products have a chance of being non-zero, just only one corresponding to the trivial identity permutation, because taken from the first row, it's almost all zeros. We can only take the first entry. Then from the second row, we have to take the second entry, and so on. So the product will be just, the only product will be the product of diagonal entries, and will be 1. That can be generalized to a more interesting matrices. So imagine arbitrary entries only diagonal above and just having zeros below. So in this case, the determinant will still be just one. The expansion of the determinant as a sum of products will have only just one product in it, the product still of diagonal entries. Again, the answer is going to be just this product, which is there in the determinant with sign plus, but nothing else will be surviving multiplying with these zero entries, because of the lower corner, lower triangle of entries being 0, the all other n factorial minus 1 products will be 0. And that is easy to see going bottom up, just starting with the last row. It's mostly zeros, so we have to take non-zero entry. Potentially non-zero entry is this last diagonal entry. That's all we can take. So we have to take the last element from the last row. After we do that, we have to look at the one before the last row, and since all columns have to be different as well, we cannot take anything from the last column, and the only non-zero entry will be just the one sitting on the diagonal, and so on. By just by repeating it by induction, we are forced to take only the entries from the diagonal in this product which we want to be non-zero. So avoiding zeros, we are only taking diagonal entries. And that is a very useful property of determinants, which will be crucial for certain computational algorithms. And here I'm going to finish with one basic property of the determinant, which we will not be proving. Proving it without certain preparation is very difficult, nearly, but yeah, it's possible, but it is unpleasant. The preparations, however, are just beyond the class content. But the property still is very crucial and will be used throughout. The property is the following. So if we take two matrices of the same size and square matrices, we can multiply them, and the result will be again a square matrix of size n. The determinant of the product will be the product of determinants. That is a very useful property. That is basically the property which brings us this answer. There is only effectively one answer for a function on matrices with numerical values having this property. And proving that and finding the answer and proving that this answer is indeed giving us a multiplicative function, as I said, is just too laborious, so we will skip it. Warnings: the determinant is far from being linear. So if we take a product of matrices, we have the multiplicativity for the determinant, but of course for the sum of matrices in general there's no relation between the determinants. Like that is almost never true. It's easy to see. We can just take the identity matrix and we can take minus identity matrix. Their sum is 0, but the determinant of the identity matrix will be 1. The determinant of the minus identity matrix will be the product of all the minuses, so will be negative 1 to the power the size of the matrix, negative 1 to the power. So this is the determinant of 0 matrix, which is of course total 0 matrix has 0 determinant. But on this side we have determinant of the identity and determinant of the minus identity. this is altogether, this is 1. This is -1 matrix. A non-zero matrix entries will be -1, -1, -1 on the diagonal, and we'll be looking at their product of as many factors as the size. So that is 0 if n is odd, but if n is even, it is not. So that is probably the easiest example right now of why determinants have no chance of being additive. More about them will come in later videos. See you then.